Welcome friends to my channel Bal Vigyan Bharti, and here is your mentor Avilash Sarkar, and we are progressing on vector collinearity and non-collinearity. We have learned several conditions for collinearity and non-collinearity, and then after followed by some examples or the problems that is related to the collinearity. We prove that if two vectors are collinear, they are following some characteristic or conditions. On that we can prove they are collinear. On the reverse, if it is given that the condition is satisfying, then prove the collinearity. If it is collinearity, then condition satisfying the other way. There may be some more kind of problem on collinearity that I came across when I am searching several problems. It's available in your different resources that I will discuss. But prior to that, today I will do a second part of that, that is vector coplanarity and non-coplanarity. So coplanarity, if I want to discuss coplanarity, that means if vectors are coplanar, that means in simple words we can understand this: if two vectors or more than two vectors are existing in a plane, then definitely they be coplanar. For any substances in any vectors which only be acting in the same plane, so they are coplanar. But one thing you have to be clear: as two lines can form a plane, similarly two vectors can form a plane. So they don't rely on other vectors if it is there. So if I assume there are two vectors only in the space or in anywhere, so they together will form a plane always. So there is no such thing that will restrict to form a plane. As you can take it similar way: if two points are there, then I make a line. The similar concept: if two vectors only exist in a space, they will always form a plane. That is the basic concept. But if the vectors, I am talking about the vectors, if it is more than two, then what are the conditions? What are the specific conditions on which we can say the three vectors are coplanar? So the basic or the simplest concept that may arise, you can think from the common sense, that if three vectors are there and two vectors, as I said, is always can form a plane, then if we can prove that the third one is consecutively coplanar or existing in the same plane with the other two vectors individually, then you can say that these three vectors are coplanar. So that is the simplest concept. But to understand that, we have to understand some generic conditions on which we can say that. So the first condition, and one more thing, that coplanar is not that only when the vectors are in a same plane. Okay, there may be several vectors which lie in a plane. If I say this is a plane 1, so that there are one such different condition or one such specific condition. If it is satisfy that also, we can say the coplanar. What is that? If I can draw a plane which is parallel to this plane 1, there we can assume several planes, or let's say I'm assuming one such plane which is parallel to that. What is parallelity? Means that two planes, they will not merge to each other ever if it is being extended either side. As like two lines, if it is parallel, they will not intersect each other if it is being merged either side. Same thing happens if it is a plane, and if I extend in either side, it will ever merge. It will not ever merge to each other. So this kind of plane is called the parallel plane. And if any vectors existing in this plane, then we can say, as per definition, say this all vectors are coplanar, even though they are residing in different plane, even though then we can say that this vector, if I name it A, B, C, D, E, F, such vectors, where A, B, C, D lying on plane 1 and E, F are lying on P2, then we can say all A to F are coplanar. So this is the basic and very much has to be understood when we discussing about the coplanarity of vectors. So this is the condition where the definition completes itself, that vectors which are in same plane or in plane which are parallel to each other are coplanar. So my definition would be the vectors which are lying in same plane or planes parallel to each other are coplanar. Okay, so this is the physical meaning of coplanarity. So mathematically, if I represent what are the such conditions, by that we can prove these are coplanarity. Theoretically, you can say this is okay if two planes in some condition, if it is given that where we can say that the vectors are existing in a same plane or in a different plane which are parallel to each other, then we can straight away say as per the definition of the coplanar. But there must be some mathematical condition on which we can derive into this coplanarity, and that also will support this definition. So we'll bring that condition right now. So the first two conditions that is there in the definition is that the vectors has to be in the same plane. So first two conditions are the vectors are to be in same plane. Okay. Second condition, they may be in parallel plane. So these are the first two conditions which we are from the definition. Third condition, this is a specific, the triple scalar product is 0. So this is the specific condition. So if I elaborate is, triple means there must be three vectors we are talking about. There's something triple scalar product is meant that I will discuss. But thing is that we will work with at least three vectors. So let me make this understand. Let's say these are two vectors. This is vector A, this is vector B. Okay, and they are making an angle between theta. So when we will discuss, there are mathematical representation of triple point vector, and there are some vectors which will let's say I'm talking about three vectors A, B and C. How they will relate, I will talk on that further. So but in that plane, in that space, there are t vectors. So it says A or rather C dot A cross B. This is the mathematical representation of triple point product. If some three vectors are related such a way कि one vector dot product to the cross vector of other two will be 0. So this is called the triple scalar product. Why triple? Three vectors involved. This is a product which is combination of dot and cross product, and the resultant is a scalar 0 that doesn't have any direction. So in all together it is called triple scalar product. So this dot product and cross product we already learned. If any two vectors, I'm talking about the general representation. If two vectors are there, this means A mod B and followed by cos of theta, where theta is the angle between A and B. And if I do the cross product of that, it will give you the mod of A, that means that only the value are taken, and followed by sin theta, and theta in this case also the angle between the vectors. Now how this resultant would act? For A dot B, it is a scalar product that will lie on the same plane. If this gives some because this is magnitude and direction both is there, if this gives something dot product, then the resultant will lie on the same plane. Let's say I'm talking about A and B, and somehow the result, this is theta, somehow the resultant is this way. It means A dot B is this way. This will lie, these field vectors will lie on the same plane. So this is dot product. For cross product, if two vectors are this A and B and it is theta, then this will follow the right hand thumb rule. That means if I take the A cross B, that means A is coming first. So from A side, I will move the thing according to the other four finger of the arm, and the resultant will be in the vertical. That means it will follow the thumb. The result will follow the thumb. If I want to represent it in a 2D plane, this will give A cross B, and this A cross B resultant will make 90 degree with both the vectors individually. Okay, so that means if I physically want to represent it, that must be towards the, if this board is the plane where A and B lies, and that resultant A cross B will be on the vertical to the board. So this way A cross B will be represented. So this is the vector which will get by the cross product. This is called the cross product, this is dot product. So dot product, the resultant will lie on the same plane, and the cross product, the resultant will be the perpendicular to the plane. Now this is the concept on which I will discuss further. So that's why I elaborated the cross and dot product. Now I will come to this. Now there are three vectors we are talking about, and if this is the triple point product equation, this expression must be equal to 0. Then only we can say that these three vectors are coplanar. Now come back to the thing we are discussing. Now this is A small a, this is B, and this is theta, and we are doing A cross B. Now see, I am just working with initially A cross B. That means A cross B, it will make 90 degree to this, this will make 90 to this. Okay, so A cross B. So that means that A cross B, the resultant A cross B, if I do, I will get this resultant, and that will be 90 degree to A and B both. Okay, now if this is equal to R, let's say, so now further C dot R. Now what would be your C? If I do C, though C, if it is like that it is on the, or rather I will commonly start with the any other vectors on this plane of AB, where AB is lying. Let's say this X. Now this X also will make 90 degree to this, 90 degree to this AB, where it is R. Now if I do R X dot R, and what is that? It will be the X magnitude, R magnitude, and the cos of theta. What theta is the angle between the X and R. Now what is that X and R? This is the same, it is the vector which is lying on the AB. If it is making 90 degree to AB, then definitely if I say this is A cross B, so any vector on this board will make 90 degree always if I take any vector. So X also make 90 degree. So ultimately cos 90 is equal to 0, cos of 90 is equal to 0. So that means this total thing will come to 0. Okay, now if it is so, that means any vector in this plane where A and B lying, and that will give you result is equal to 0, that means ultimately this is what A cross B is equal to 0. If instead of x I can take any vector that I have assumed or presumed that this is another vector is lying on the same plane, then I can say this is equal to 0. So that means this is only can be 0 for any other vector other than A and B on the same plane, the result will be 0. So C must be on the same plane. If I want to say that C is lying on the same plane, then this result will be 0. And now if I say if result is 0, C definitely be on this plane, because unless and until C in the same plane, that angle theta won't be 90 degree. If I say that this is making C and this is vertical, so in this angle, if I say this is angle, so if it is not make on the same board, so I won't get the angle 90. So if it is not 90, then this will not come 0. So definitely C is lying on the same plane as A and B. So from that, if I can calculate that if it is 0, then C must lie on the plane where A and B line. So we can say A, B, C are coplanar. Okay. So this can happen if I say this equation may be written is in any other form. That means if I say C dot A cross B is 0, then this is also 2A dot C cross B also 0, or B dot C cross A also 0. Okay. Okay. If I say A, B, C, then A dot C cross B, A dot C cross B, then this case this is the resultant. In this case, if it is the, so what this will go this side, and this side, this case it will be piercing the board and going to the other side. Then also that resultant will make 90 degree to A, so this will be 0 then. Okay, so that doesn't make any changes if I take any order of this. Now we know that what is A cross B. A cross B is your, if it is A being represented, now if I assume the A being represented by A1I, A2J, A3K, there are three components with if in Cartesian plane, if I represent the vector A like that A1I, so these are the components on in X and Y Z direction, and all together it is A. Similarly, B can be represented B1I, B2J and B3K, and C can be represented C1I, C2J and C3K. Now what I am saying, if I am taking this one, just forget about this other two, A cross B. So what is your A cross B? Cross product of that will get A1, A2, B1, B2. Okay. Now if I do C dot with that, so C means here, sorry, I have to take another, the third component also, B3. That will be like that only, where the first row will come as I, J and K. This is the cross product. This is a result of cross product. Now if I do C multiplication, ultimately this will become C1, C2, C3 first row, A1, A2, A3 second row, B1, B2, B3 third row. This will come. That I can show you when I will discuss about the chapter matrix. When three things are being calculated in this equation, then this is the end result. Now you understand, when C is coming first, the first row will be C, it is in second position, second row, and this way it will come. So ultimately, if I break into the thing, so ultimately I have to take it in a sequence so that you can remember it for easiest way, so you can remember it easily. So I am taking it in this manner so that you can remember it. A come first, so ultimately this is become A1, A2, A3, B1, B2, B3, third one C1, C2, C3, this equal to 0. Now how will I break it up? This will come as this first row when I take, so I have to abolish this one, only this will be cross multiplied in that sequence. So A1, the matrix will be B2, B3, C2, C3, then the next one will be minus, A2 will be the coefficient, and the matrix will be B1, B3, C1, C3, the next again plus A3 will be the coefficient, and for that B1, B2, C1, C2. So this further you can break by multiplying cross, okay, and in between there will be sign. So what will be there? A1, B2, C3 minus C2, B3 minus A2, B1, C3 minus C1, B3, and the last one is A3, B1, C2 minus C1, B2. This will be the end calculation. Whichever way you want to remember, you can remember. If it is this comfortable for you to remember, further if you know the process, you can easily bring it to this form, or if you want to remember in this way also, you can remember. So anyway, it has to be like that the result has to be 0, then it is a coplanar. Okay, this is called triple scalar product. So the next condition, if the vector, so the fourth condition, I come across third condition. Fourth condition is that for n vectors, means there are n numbers of vectors, if any two, not more than any two, if not more than two vectors are linearly independent. So this is the condition. If there are n numbers of vectors, if not more than two vectors are linearly independent, then the vectors are coplanar. So to understand this is very much confusing. So let me understand one by one. These terms I have already established or make you understood or explained several times. Again I am explaining. Let's say the one such linear combination of vectors, let's say A1 x1, A2 x2, and there are as n vectors xn, is such a way that A1 is equal to A2 is equal to A3 ... is equal to An is equal to 0. That means these are the coefficient. This is scalar coefficient. Okay, this is scalar coefficient, and if all scalar coefficient, the first condition that if all scalar coefficients are individually 0, where we can express a vector linearly in linear combination. Here another condition that x1, x2, all vectors are non-zero, and yes, all vectors are non-zero. This is the condition. Now if any linear combination is possible and this linear combination is possible and the resultant is 0, means this will give you some vectors na, because this is a vector being added with a scalar, so ultimately I will get a vector. This vector when the linear combined is 0. Okay, so that means there must be something they are following, polygon law, and this polygon law is making the resultant 0. So this resultant 0 and individually all the scalars are 0. Then this condition is called trivial or linear independency, you can say. So let me explain. If all x1, x2, x3 up to xn such vectors can be combined in a linear form and the resultant is equal to 0, and all the coefficient, that is the scalar coefficient that has only the magnitude not the direction, all scalar coefficient individually with 0, then these are called the trivial condition, and this trivial condition is also called the linear independency. Now here for the end vectors, if not more than two vectors are linearly independent, then we can say that all end vectors are coplanar. How can I say that? If it is linear independency, then we know that for vectors which are in same plane, and for I'm talking about the collinearity, if it is in same plane and not making not in same line or parallel, then the vectors, this kind of vectors which are making an angle and lying on the same plane, then these vectors are linearly independent. Okay, this is the condition where the vectors are lying in same plane, but in this condition they are not supposed, if they are being supposed to be in same plane, then there is no point of proving that they are non-coplanar, they are coplanar. In this case there must be something where that vectors in that coplanarity, the initially you discussed, the vectors are, if it is lying on the same plane or parallel plane, then only you can say that vectors are coplanar. But if say the planes are not parallel to each other, rather making an angle, okay, they are intersecting somewhere, and the vectors lying in this plane are not coplanar. So for this case I am saying the condition, the fourth condition has to be proved that they are coplanar. But the condition of linear independence, you understand? Now I assume some plane where n minus 1 all vectors are there, and another plane where only one vector is lying. Okay, now individually if I want to see the vectors, let's say there are vectors, if one a, b, c is there and d is there. Now if I can prove that a and d it is linearly independent, that means linearly independent means that vectors are not parallel to each other, at least that there could not be possibility of collinearity because they are lying in the different plane, that we know. If the vectors are not in same plane, they are not collinear, but they are not coplanar, that I cannot say. So if I can assume that a and d are non-coplanar and not lying in the same parallel plane, then a and d are linearly independent, but means they are not parallel to each other. Now if it is this pair is satisfying this, now I am talking about b and d. So the b and d also, if I can say that they are linearly independent, this is linearly independent, this is also linearly independent. So there you can say this, the definition says not more than two vectors will be linearly independent, but here you can say a and d are linearly independent, b and d are linearly independent, because if they are in the same plane or a parallel plane, then only they are coplanar. But I am assuming some plane which is not making coplanar, means parallel plane. So this A and D will be linearly independent, and the same if it is lying A and B and C are lying in the same plane, B also be linearly independent with that. So from that it is always, and C and D also linearly independent, but our maximum flexibility is for two vectors. I can go up to two vectors which are linearly independent, but here more than two. So you can see even after one single vector is not in same plane, the other vectors in combination are linearly independent. So from there you can say, even if it is, if you allow one vector to be other plane which is not parallel, this condition cannot be satisfied for n vectors. Out of n vectors, I am taken n minus 1 is in the same plane, 1 is the other plane. So all this n minus 1 in combination of the one vector will be linearly independent. So this condition will not satisfy. So I cannot allow any vectors to be other plane. So from that reverse we can say, if this condition satisfied more than 2, then all vectors are not coplanar. So if it is up to 2 vectors or less than 2 vectors, then we can say that n vectors are coplanar. Understand my point? This is the explanation. If what you have assumed, we have assumed one vectors the other plane which is not parallel to that, and from there other combination will be non-collinear. Obviously this is common sense. So if it is so, then it will not satisfy the condition. So it cannot be another plane. So all vectors will be in same plane. This is the concept. So this is the fourth condition. This is bit tricky, but when you will solve any problem on that, it will further will be easier to understand. Okay, so wait for the sum, but I will discuss in later. Yeah, fifth condition, if it is 3 non-zero, means that must be non-zero vectors. I cannot deal with the zero vectors and I cannot establish this conditions. If 3 0 in 3D space, then it is if it is collinear, then all are linearly dependent. That means linearly dependent. So this is also a condition of coplanarity. If 3 vectors, non-zero vectors are linearly dependent, then these 3 vectors we can say are coplanar. So linearly dependence means the same. If the vectors can be represented as linearly, all such vectors of here I will talk about only the 3 vectors. That means a1, sorry, this case I will make a plus x y z c. If it is linearly expressed, can be linearly expressed, and x y z are scalar. This case this is not a vector, I am talking about ABC. So 3 non-zero ABC vectors in 3D space, if linearly dependent, means the coefficients linearly dependent, the coefficient should be, all sum of the coefficients should be 0 altogether, and any one of x, y, z not equal to 0. This is the condition of linearly dependency. If they can be expressed in such a way that x plus y plus z is equal to 0 for 3 vectors I am talking about, and any of this x, y, z is not equal to 0, that means scalar sum is 0 and any of the scalar is not equal to 0, then this is linearly dependency. This is condition of linearly dependency. If it is satisfied, then these 3 vectors are said to be in coplanar. Okay, so this is the fifth condition. So sixth condition, that if it is given 2 vectors, so 2 vectors always in a plane. So we need not to prove it, because any 2 vectors will make a plane always. So this is a universally truth. And so that's all. So these are the these are the condition for collinearity, coplanarity. Now, if I talk about the non-collinearity, the reverse of that, non-coplanarity, the things are different. So that means they are not in same plane. Just I'm taking the reverse condition of the coplanarity, not in same plane. They are not even in parallel plane. So these are the first two conditions for coplanarity. So this reverse of that, they must not so they are not in parallel plane and not plane. So they are in a plane which are making angle, means diverging or converging plane, where if it is extended in either side, any of the side or either side, they will meet some point. They will meet at some point, and their intersection will be somehow, it will be a line segment. Okay, that will merge at the line. Okay, so like that plane. And the third condition, that triple point, this A dot B cross C, if I say, is not equal to 0. Fourth condition was that if n vectors are there, for n vectors more than 2 vectors are linearly independent. Okay, so this is the fourth condition. Fifth condition, for 3 vectors in 3D space are linearly independent. Okay, so that's all for non-collinearity, just reverse of the conditions. So this is for now. I will end up here in this session. In the next session, I will move on to some example on this coplanarity and planarity. Maybe some on the collinearity also I will bring, because that is a kind of problem that I find it is different to the problem that I have already discussed. Okay, so let me give me some more classes on this. Then after I will move to next subjects. Okay, so keep on seeing my videos, and if it is possible, subscribe my channel. Thank you.